So in this module, we're talking about modern quantum mechanics, the quantum mechanical model of the atom, and specifically what's called Schrodinger's equation, Heisenberg's uncertainty principle, and wave functions. So Bohr did a really good job of being able to describe a hydrogen atom. He could calculate the ionization energy, he could calculate the line spectra, but his model didn't work for other atoms. Hydrogen and hydrogen-like atoms it worked for, but once you put more than one electron in there, his model no longer worked. So there was a lot of work done into trying to come up with a model that could, deal with atoms other than hydrogen. And that's where all this stuff came from. So we now use what's called Schrodinger's equation. This is Schrodinger's equation, and it's not as simple as it looks, but fortunately we don't have to solve it in this class. H is called a Hamiltonian, it's an operator. Psi is called a wave function. We will talk a little bit about wave function. E is the energy, and psi again is the wave function. The important thing about Schrodinger's equation is that one of the things that we get out of Schrodinger's equation when we solve it are, well, we get multiple solutions for a given atom, and we get these wave functions. Now, you'll see in a minute what those wave functions tell us. But another really important idea that came along right along that time, around early 1900s, was Heisenberg's uncertainty principle. And Werner Heisenberg proved that no matter how good of a tool we have, there is always some uncertainty in any measurement we make. And we cannot know anything exactly that is. So he said it this way: the uncertainty in the position, in one dimension it's delta x, and 3 would be like x, y, z, or whatever. But the uncertainty in the position, delta x, times the uncertainty in the momentum, mass times velocity, has to be bigger than or equal to some number, Planck's constant divided by 4 pi. Now, Planck's constant is a really small number, but it's not zero. And so there's a lot of implications from Heisenberg's uncertainty. Now, the minimum uncertainty, the best we can do, is when this is an equal sign. And most of the time it's going to be bigger than that. But this is a bottom limit. So let's look at this real quickly. Momentum, mass times velocity. A lot of times we know the mass pretty well. So it really comes down to the uncertainty in the velocity, the speed, and the uncertainty in the position. What this says is that the closer we know where something is, the less we know about how fast it's moving or its momentum. And vice versa. The more we know about its velocity and momentum, the less we know about where it is at any given time. We're going to apply this in particular to an electron in an atom. So here's a little example. We're going to use the Heisenberg uncertainty principle to calculate the minimum uncertainty in position, delta x, for an electron whose uncertainty in velocity is 5.19 meters per second. So we're going to use Heisenberg's uncertainty principle, making this an equal sign. That will give us the minimum uncertainty, the bottom limit. Rearranging this, solving for delta x, we get h over m times delta v times 4 pi. I move the m outside of the delta because we know the mass of an electron to many sig figs. So plugging in the numbers, again, Planck's constant, which you've memorized, the mass of an electron, the uncertainty in the velocity, and times 4 pi, we get 1.12 times 10 to the minus 5th meters. Now, if this were an electron in an atom, hydrogen atom's on the order of an angstrom, 10 to the minus 10th meter. So this is 5 orders of magnitude bigger than that. All right, so it ends up, okay, for an electron in an atom, we can never know really where exactly it is in that atom. The best we're going to do is say that we know that with a given probability, that electron is in this given region of space in the atom. Okay, that is, with say a 90% probability, we know it's in this somewhere in this volume of space. And we can define that volume however we like, and we can set the certainty any way we like. 90% probability. The only thing is, if we go to 100% probability, then The only way we can do that is go out to infinity. Watch. So, first of all, the probability of finding an electron in an atom in a given region of space is called an orbital, and it's given by the wave function for that electron squared. Now, this is what we call, if we make a graph of the probability, this for probability psi squared versus r, the distance from the nucleus, it looks like this. This r squared, this big one here, by the way, that's because we're just taking the radial part of this wave function into account, how far it's from the nucleus. And it looks like this. This curve, this line, asymptotically approaches the x-axis as r goes to infinity, which means that it never gets to probability of 0 until we get out to infinity. In other words, that any distance from the nucleus out to infinity, there's some non-zero probability that the electron is there. That's why we have to cut it off at something like 90% or 95%. Then all of a sudden this distance gets really small. This picture up here is another way we have of representing this probability distribution. The greater the density, imagine this is being made by a bunch of really small like dots, like taking a pen and just marking it. The greater the darker the region, the greater the density, the greater the probability of finding an electron. We also talk about the probability as the electron density. The greater the electron density, the greater the probability of finding an electron in that region of space. So psi squared gives us the orbital, which is the region of space where there's a high probability of finding an electron. And the probability asymptotically approaches 0 as r goes to infinity. Now, we can draw a different graph called a radial probability distribution function. And if you imagine we're talking all about the hydrogen atom right here for now still. If you imagine the atom as being layers like of an onion as you go out from the nucleus, if you multiply the probability of finding an electron in each of those layers times the volume of that layer, you get the radial probability distribution function, and it looks like this. Okay, now it doesn't go up to, doesn't get really big as r goes to 0, but rather goes to 0 at r equals 0, and again asymptotically approaches the axis as r goes to infinity. This is because as you get closer and closer to the nucleus, the volume is smaller and smaller, and so because you multiply the probability times the volume, as the volume gets small, the probability also gets small. And this is a pretty good picture right here. If you imagine taking this curve and rotating about each of the three axes, say about this axis here, rotate it, this axis here, and then the axis coming out here, rotate it that way around it, and looking at it from the outside, what you would get would basically look like a sphere. We'll come back to that later. One more thing here. The maximum radial probability for the hydrogen 1s, the maximum of this curve, ends up at being 0.529 angstroms. We call this the Bohr radius. And what that corresponds to is the distance from the nucleus where you have the greatest probability of finding an electron in a hydrogen atom. Doesn't mean it can't be anywhere else, just that's the greatest probability.